Hello, my name is Kevin, and this is Lab Group 3B on Tuesday mornings. We're doing lab number 4 today. My role in the lab is for setup and collimation of everything to start out with. So in the first part of the lab, we were setting up and aligning our capillary and beam expander, which starts by aligning a Heaney laser with the rail, and then using a microscope objective, which has a 9mm focal length, followed by a spatial filter, which is 20 microns in size, which we calculated using this formula right here. We align the spatial filter along the X and Y axis by using these little adjusters here in order to get the beam straight through the center of it, clean beam that is. And we used a 250mm collimating lens, which we calculated to have a beam expansion ratio of 27, which is necessary in order to fill the 2-inch aperture of the shear plate. And then we aligned it with the distance between the two lenses by moving the collimating lens, and you can tell by looking at the top of the shear plate when the interference lines are aligned with the reference line. That's when you know that you have a collimated beam coming out of it. Pause. The orientation of our collimated lens, we had the curved side facing away from the microscope in order to minimize spherical aberration. You can see that the lines are pretty much parallel here. And then if we switch the lens around so that the curved side is facing towards the microscoped objective, and then we align it again, you can see that the lines are a lot more curvy, which means they have more spherical aberration. Yeah.
Hey, I'm going to talk very quick about shear plates. So we have two types of shear plates, plane parallel and wedge. So with plane parallel, what we're going to see is fringes or just uniform. Uniform mean collimated, and fringes mean we're not collimated. And wedge, we're going to see situation of the fringes change the orientations. By measuring alpha, D, and shear distance, we can calculate focal length of the mirrors or lenses, and that's our main application for this lab. The sensitivity and the visibility of shear plates depend on the index of the shear plates, the wedge angles, the diameters of the shear plates, and the thickness of the shear plates. So this is the picture of showing converging fringes look like this. Collimate have to be long horizontal, and diverge have to look in this direction. Aberration measurement can be used in the shear plate, and it is actually a slope measurement, as you see over here. So instead of you see the 4th degree angle, 4 degree, you're going to see 3 degree for spherical aberration.
So in this part C of the lab, we wanted to measure the focal length of a low power mirror, and we did this by putting the mirror behind the shear plate, and then we took measurements of the shear distance, the fringe spacing, and the deviation angle relative to the reference line at 2 different locations, and we used these measurements to calculate the radius of the wavefront. And then we used that measurement in addition to the distance between the mirror and the viewing screen, which is L here. We used those to calculate the radius of the mirror. One difficult part in this lab was trying to get the, if you look at the viewing screen here, it's trying to get the shear distance. You see, because it's such a long focal length mirror and it's actually not a perfect sphere, then it's very difficult to measure the shear distance. So one thing we did in order to help that was move the shear plate up and down, which kind of increased the distance at some point between the beam footprints.
So for part D, we were told to insert a low power lens between the collimation lens and the shear plate. And if you view the shear plate here, as we do that, the fringes are deviated about 50 degrees, and that is alpha. So alpha has increased to 50 degrees. The fringe spacing, D, has also decreased as a result from 5mm to 3mm. You can also tell that the fringes have rotated clockwise, which means it's inside focus. And if we take a look at this equation right here, basically what we've done by inserting the low power lens is we've decreased R, because it used to be a plane wavefront. So we expect to see that D has decreased, and then the shear distance decreased from 9mm to 7mm as well. In addition, by decreasing R, we have increased the OPD, which we have also seen. Pause.
My name is Fa. I'm going to continue with part E. in this part, we will insert the mirrors on the rail, and we try to measure the radius of the mirror by focus the beam, go to the reference lens to the surface of the mirror, and you can see it's go back, so it's collimated when it go back here. So the fringe is parallel to the reference line. So I move the mirror down the rail and look at the space, the fringe on the shear blade, and I can see where it's parallel back to the reference line. It's collimated back. So I record the two distance, and we subtract that, and we got the radius of the mirrors is 200 millimeters, and f we divide by 2, we got 100 millimeters, and you can see it's add some spherical operation to the system because it go back to the system through the second surface.